CodeR, issue resolving with multi-agent and task graphs, Preprint. Hawaii Company, Chinese Academy of Science, Singapore Management University, and Peking University. Abstract. GitHub issue resolving recently has attracted significant attention from academia and industry. SWE-bench is proposed to measure the performance in resolving issues. In this work, we propose CodeR, which adopts a multi-agent framework and predefined task graphs to repair and resolve reported bugs and add new features within code repository. On SWE-bench Lite, CodeR is able to solve 28.33% of issues when submitting only once for each issue. We examine the performance impact of each design of CodeR and offer insights to advance this research direction. Introduction. The rapidly growing capability of large language models, LLMs, is dramatically reshaping many industries. The most recent release of GPT-4o demonstrates a significant leap in the multimodal capabilities and artificial intelligence, AI-human interaction, whilst maintaining the same level of text generation, reasoning, and code intelligence as GPT-4 Turbo. LLMs can interact with humans and the world as humans do. It is considered a starting point for LLMs to take over tasks from humans or collaborate naturally with humans. Issue resolving is one of the software engineering tasks experimented with LLMs that is particularly relevant in practice. SWE-bench collects 2,294 real-world issues from 12 popular Python libraries. The LLMs are tasked to resolve the issues based on a given issue description and the whole repository. This task is extremely challenging due to the need for deep reasoning about a huge amount of code and incomplete information for the task description. SWE-bench Lite removes the issue with low-quality descriptions to make the task more addressable, yet it remains highly non-trivial. Since SWE-bench was released, multiple approaches have been proposed. SWE-llama adopted a pipeline with retrieval-augmented generation, RAG, to generate the patch directly. Later, AutoCode Rover added code contextual retrieval with keywords in the issue description into the pipeline. It iteratively collects code context by the keywords in the issues until LLMs have connected enough information to generate a correct patch. Instead of explicit patch generation, SWE-agent performs iterative edits in the repository. It then uses git diff command to generate patches, which avoids patch format errors. In the literature on applying LLMs for solving software engineering tasks, multiple agent-based approaches have shown their competitiveness. For example, MetaGPT uses the multi-agent approach to automate the software development process from scratch. AutoCode Rover and SWE-agent use the single-agent approach to address automatic GitHub issue resolving. To the best of our knowledge, in issue-resolving scenarios, the agent-based approaches primarily focus on a single agent. Moreover, previous works performed task decomposition on the go, with each subsequent step being determined by the preceding one. Multi-agent possesses the advantage of better decoupling each role and leveraging contextual information. However, implementing a multi-agent framework in issue resolving presents challenges, such as 1. Free communications between agents may lead to a non-progressing loop without termination. 2. Information passed from one agent to another may incur information loss. 3. Complex plans are hard to follow when multiple agents are involved. We remark that these problems are not unlike those when human developers collaborate. In this work, we develop a multi-agent design called CodeR that effectively addresses the above-mentioned problems. CodeR adopts a multi-agent framework and a task graph data structure for issue-resolving tasks. Our design is based on the following intuitions: less candidate actions, easier decision. We introduce a set of diverse actions for different purposes. The number of actions is much larger compared with the single-agent framework such as SWE-agent. To address the problem of a large number of actions, we reduce the complexity of making decisions for the next action by limiting each agent's focus to a subtask and a subset of associated actions. Look before you leap. We believe that planning at the beginning of the pipeline is better than deciding the next steps on the go. Moreover, a good plan should consist of small and manageable tasks that LLMs were trained to solve. bypassing instruction following and memorization. The conventional plan generated by LLM is in the form of plain text. It is usually placed in the prompt to guide the subsequent steps in an LLM-censored system. It requires the LLM to have a strong instruction following capability and to have a good memory to execute the plan precisely and iteratively. For complex tasks like issue resolving with complex tools, task plans in pure text prompts will be hard to follow. Therefore, we introduce a new data structure, namely task graph, that can ensure that all pre-designed plans are accurately followed and executed. Our contributions are as follows. 1. We propose CodeR, a multi-agent framework with task graphs for issue resolving. Inspired by the issue resolving process by humans in the real world, we design the roles and the actions. For plans, we design a graph data structure that can be parsed and strictly executed. It can then ensure the exact execution of the plan and at the same time provide an easy-to-plug interface for plan injection from humans. 2. We leverage LLM-generated code for reproducing the issue and the tests in the repository, excluding the verification tests, to get code coverage information. Coverage information improves contextual retrieval based on the keywords in the issue text and does fault localization together with BM25. 3. We renew the state-of-the-art of SWE-bench Lite to 28.33%, 85 out of 300, with only one submission per issue. Section 2. Framework. As Figure 1 shows, our design contains 5 agents, which can collaboratively solve GitHub issues. Manager. The manager is an agent who interacts with the user directly and is in charge of the whole issue resolving task. It has 2 responsibilities. 1. Selecting a plan according to the issue description. The plan specifies the agents involved and how they should interact to finish the task. 2. Interpreting the execution summary of a plan. If the execution summary has indicated that the issue has been solved, it will summarize the change and submit the patch. If not, it will come up with a new plan or give up. Reproducer. The reproducer is an agent that is responsible for generating a test to reproduce the issue. If the issue description contains a complete test, the reproducer only needs to copy the test into a new test file, reproduce.py, and execute and compare the output. But this is usually not the case for real-world issues. The reproducer often needs to adjust or generate test cases. We generate test cases by extracting test inputs from the issues and using LLMs to generate test sequences. Fault localizer. The fault localizer is an agent that identifies the code regions that could cause the issue. It is equipped with several fault localization tools in software engineering. Editor. The editor is the one who performs the actual code changes. It will utilize all information provided by other upstream agents and will gather contextual information with autocode reverse search. With enough information gathered, the iterative edits, same as SWE agent, will be performed. Verifier. The verifier is an agent that will run the reproduced or integration tests to check whether the modification has resolved the issue or not. For actions, we reuse the actions that are defined by SWE agent and autocode rover as Table 1 shows. Besides, we also introduced new actions 0 and 18 through 21. Action 0 selects or generates feasible plans by analyzing the current issue. Action 18 retrieves the top 1 similar issues and its corresponding patch by description. Note that we prompt the agent to check whether the retrieved result is relevant to the current issue and analyze how its patch solves the retrieved issue. Action 19 performs fault localization described in section 3.2. Action 20 runs the reproducer generated test and the integration tests. Same as ADER, the integration tests do not contain the test to verify the correctness of the generated patches. Action 21 summarizes all actions performed and observations by each agent for a subtask. Action 22 provides basic Linux shell commands such as cd, ls, grep, and cat. we assign a unique set of actions to each role, similar to how different roles in the real world possess distinct skills. For example, only the manager has permission to the plan and submit actions. All roles are granted permission to use the basic shell commands action. Section 3. Methodology. Repository-level tasks usually require processing a huge amount of information and taking many steps before reaching their desired solutions. Existing works show that dividing a repository-level task into a set of connected subtasks and conquering them one by one could be effective. Parcel and CodeS focus on generating a large piece of code for complex algorithms and simple repositories. Both of them utilize inherent program structures like call graphs or file structures for task decomposition. Issue resolving is also a repository-level task, but is closer to a modification task rather than a generation task. In addition to generating code, a repository-level modification task requires identifying the correct locations before generating the correct code. It is unfeasible to use a whole repository as input context. This introduces additional steps and complexity which require a more powerful framework for planning. 3.1. Task graphs for planning. The description of GitHub issues is extremely diverse. Some issues only have one sentence in natural language. Some may provide the test code, running results of the test code, and a possible solution. Besides descriptions, the solutions of issues are also varied. Some could only require changing one or two lines to resolve, making the task similar to a line completion task with context, while some could necessitate changing multiple files, requiring a deep understanding of the code semantics within the repository. For similar issues with clear descriptions, their solutions are obvious and can be figured out at first glance. But for complex ones with ambiguous or inaccurate descriptions, executing tests and searching through the codebase or web could be beneficial for solving them. To cope with different approaches to solving the issue, we design a task graph that can easily add new plans. It can also be strictly followed by multi-agent systems. Figure 2 shows a task graph plan in JSON format. It specifies a collection of plans on the top level with the name Plan ID. For each plan, entry specifies which agent to start with. Roles specifies a list of agents that are involved in this plan. Each selected agent will be given a subtask specified in task. Once finished, all actions that the agent performed will be summarized and passed to its downstream according to the result of the current subtask. Plan A in Figure 2 involves 4 agents: reproducer, fault localizer, editor, and verifier. This plan starts with reproducer as demonstrated in Figure 1. This design of plans decouples agent design with task decomposition. When designing the agents, one can only focus on the high-level goal of a subtask without considering the details of the diverse approaches. The diversity of approaches can be specified and adjusted in the field of task and downstream. In this way, the plans can easily be added, deleted, and tuned without changing a single line of code for agents. Plans in Figure 2 will be parsed into a graph with an entry node specified by entry. When starting to execute the plan, the entry node is activated and the specified agent will start to execute its subtask using the React framework iteratively. Once finished with its subtask, it will activate one of the specified downstream nodes. Agents in the plan may be activated multiple times if there is a cycle in the plan. The plan finishes when the manager is activated or exceeds our budget. We have designated 4 plans as Figure 3 shows. Plan A is shown in Figure 1, which is a standard flow to resolve an issue. It has no loop for simplicity and robustness. Plan B tries to resolve the issue directly for simple issues. Plan C adds a loop that allows the feedback from testing. This circle is also used by ADER with tests that are not related to the issue, which are also called integration tests. Plan D takes a test-driven approach with a ground truth test for issues, such as fail to pass and pass to pass tests in SWE-bench. In our experiments, We only use plan A and B for cost savings and fast evaluation. 3.2. Fault localization specialized for issue resolving. We leverage fault localization techniques to provide precise location information. A previous work shows that the use of fault localization techniques leads to an increase in the efficacy of resolving GitHub issues. We notice that the agent is allowed to run test suites, but only the results are used, while runtime information is not captured during the process. Test-based fault localization can provide precise location information based on runtime information, and specifically, we use spectrum-based fault localization, SBFL, as the main fault localization method. SBFL is a lightweight, test-based fault localization technique. Given a test suite that contains at least one failing test, SBFL collects statement coverage for the test suite. Suspiciousness score is then calculated based on coverage data, and all covered statements are ranked by their suspiciousness. Suspiciousness score can be calculated by different formulas such as OCI and Tarantula. These formulas share the same motivation that the fault localization should possibly be covered by more failing tests and fewer passing tests. One main limitation of SBFL and many other test-based fault localization techniques is the need for failing tests. In practice, a failing test is often not available at the time when an issue is raised. Since the reproducer can create reproduced test cases, we select the failing tests and collect their coverage data. This coverage data is also used to guide the search action. Note that if reproducer fails to generate any test script or its coverage data cannot be collected, e.g. the test script uses system calls to invoke certain CLI, SBFL will not be used as no result can be produced by it. Besides test information, issue descriptions can also be used to better localize the fault. The retrieval algorithm provides a simple yet effective way to combine text from an issue description and code from the repository. Jimenez et al. Also use a BM25 retrieval algorithm to provide file-level localization. As the information source from the retrieval algorithm and test-based fault localization, say test coverage and issue description text, differs a lot, we notice that these methods could be combined to provide better fault localization results. A previous study shows that combining multiple fault localization methods can achieve a better result than any standalone method. We use a simple linear combination here to calculate the final suspiciousness score from both methods, where score OCI is the suspiciousness score from OCI formula and relevance BM25 is the BM25 relevance score for the file FI. To choose a proper value for the combination factor lambda, we experiment on a small subset containing 10 issues that can be successfully reproduced. The result shows that almost all values between 0 and 1 yield the same result and are all better than taking lambda equals 1 or lambda equals 0. The reason for different lambdas having the same result is that many locations can tie to others with respect to a single metric. Statements that are covered by the same number of passing tests will have the same score OCI, and the statements in the same file will have the same score BM25. Both metrics could serve as a tiebreaker to each other, resulting in better result than each standalone metric. We pick lambda equals 0.99 as our final setup in subsection 4.2. We conducted an experiment on the issues that are successfully reproduced by reproducer. This means a running Python script is generated for reproducing the issue. 140 issues remain after this filtering. Coverage data collected from the script is not empty. This means that the reproduced script has at least covered one file in the project. 104 issues remain after this filtering. The result of different lambdas are listed in Table 2 and 3. From this result, we can see that combining BM25 score with SBFL can greatly improve precision by more than 10%. We use method-level fault localization as it provides enough information for the agent to edit the file while keeping good precision. The way of constructing a prompt for fault localization results is shown in the appendix Figure 11. 3.3. Prompt Engineering. CodeR includes 5 roles: Manager, Reproducer, Fault Localizer, Editor, and Verifier. To enable LLMs to play different roles, we set up system prompts and instance prompts for each agent role. The system prompt primarily describes the definition of role identity, role responsibilities, and corresponding actions. The instance prompt mainly includes the raw issue and important tips for resolving this issue. We have put system and instance prompts of 5 roles into Appendix Figure 4.13. We designed these prompts inspired by SWE-agent. When multiple agent roles communicate, they use the prompt template shown in Appendix Figure 6. Detailed prompt engineering designs for CodeR can be found at NL2 Code CodeR GitHub repository. Section 4. Experiments. 4.1. Experimental Setup. Benchmarks. SWE-bench is a benchmark that can test systems' ability to solve GitHub issues automatically. The benchmark consists of 2,294 issue pull requests pairs from 12 popular open source Python repositories, e.g. Flask, NumPy, Matplotlib. SWE-bench's evaluation can be executed by providing unit test verification using post-PR behavior as the reference solution. SWE-bench Lite is a subset of SWE-bench which is curated to make evaluation less costly and more accessible. SWE-bench Lite comprises 300 instances that have been sampled to be more self-contained with a focus on evaluating functional bug fixes. More details of SWE-bench Lite can be seen at swebench.com/lite.html. In this work, we focus on SWE-bench Lite for faster, easier, and more cost-effective evaluation. Metrics. We evaluate the issue resolving task using the following metrics: resolved percent, average request, and average token cost. The resolved percent metric indicates the percentage of SWE-bench Lite instances, 300 in total, that are successfully resolved. Average requests and average tokens cost represent the average number of API requests per issue and the average consumption of input and output tokens and the corresponding costs. CodeR's comparative methods. Recently, several commercial products addressing issue resolving have been released, but their technical details have not been disclosed. The following describes their functionalities. Devin, from Cognition AI, is capable of planning and executing complex engineering tasks that require thousands of decisions. It can recall relevant context at each step, learn over time, and fix program bugs. Devin can operate common developer tools within a sandbox environment, including the shell, code editor, and browser. Additionally, Devin can actively collaborate with users, report progress in real time, accept feedback, and assist with design choices as needed. Amazon Q Developer Agent from Amazon is a generative AI-powered coding assistant that can help you understand, build, extend, operate, and repair code. OpenCSG Starship is committed to providing a complete model data management and application building platform for large model application development teams. Based on it, they developed CodeGen Agent, which can resolve GitHub issues automatically. ByteDance Mars Code Agent is an AI coding assistant powered by GPT-4o, developed by ByteDance. Designed for multi-language support within IDE environments, it can reset repositories to undo previous modifications. SWE-bench Lite requires generating patches to resolve GitHub issues. One possible approach for LLMs is to generate the patch directly, explicit patch generation. Retrieval-based approach first retrieves the files that require editing and then adds the retrieved content to the LLM's context. Finally, the LLMs generate the patch. In the experiments, LLMs used include GPT 3.5, GPT-4, Cloud 2, Cloud 3 Opus, and SWE-llama. AutoCode Rover leverages advanced code search capabilities in software engineering to extend the model's modeling context, thereby further improving the accuracy of patch generation. Besides using LLMs to generate the patch directly to fix issues, another approach is to edit and modify the buggy code repository and then use git diff to automatically obtain the patch, implicit patch generation. SWE-agent is an automated software engineering system that uses LLMs as one agent to solve real-world software engineering tasks. It introduces a new concept of the Agent-Computer Interface, ACI, which enables LLMs to effectively search, navigate, edit, and execute code commands in sandboxed computer environments. Aider is a command line tool that pairs with LLMs to edit code in your local Git repository. Aider can directly edit the local source files and commit the changes with meaningful commit messages. Aider now works well with GPT 3.5, GPT 4o, Cloud 3 Opus, and more. 4.1.1 Implementation Details. Hyperparameters of inference. In our multi-agent framework, each role is considered a distinct agent with its own experimental settings, which include the model and history process window size. All roles are provided access to GPT-4 Preview 1106. The manager role utilizes nucleus sampling during inference with the temperature parameter set to 0 and top P to 0.95. It employs full history with a file viewer's window size of 100. The reproducer role similarly uses nucleus sampling, but only incorporates the last 5 histories. Both the fault localizer and tester roles follow the same settings as the reproducer. Finally, the programmer role, while sharing the same nucleus sampling parameters, includes a demo in addition to the last 5 histories and file viewer's window size of 100. This setup ensures a reduction in repetition and maintains the unique functionality of each role. In addition, we set the maximum cost to $8 per issue. Other details. In fact, it is impossible to have a consistent evaluation environment for all currently proposed approaches. We make some adaptations to the evaluation environment released by AutoCode Rover and use it as our evaluation environment. We reproduce all other approaches with our environment for fairness. However, the evaluation on repository AstroPi and Request still has some environmental problems remaining. In our inference environment, commands like edit occasionally trigger a container crashed error, which interrupts the process. If this occurs, we restart from the beginning of the pipeline for this issue. We pre-construct an environment completed Docker image offline to avoid wasting time on real-time installation during inference. Additionally, we divide the SWE-bench Lite into 6 processes for parallel inference to further accelerate this process. When Fault Localizer runs the repository's integration unit tests, it sometimes adds or modifies files within the repository, and we restore these files after the localization process. 4.2 Results. Table 4 shows CodeR's performance on SWE-bench Lite and its comparative methods. The results show CodeR establishes a new benchmark record on SWE-bench Lite, achieving the best performance to date compared with all other commercial products and methods. In SWE-bench Lite, CodeR resolves 28.33% of issues in one attempt, addressing 84 of 300. In contrast, SWE-agent and GPT-4 and Aider solve 18% and 26.33% respectively. This proves that CodeR's meticulously designed roles and actions are highly effective. We noticed that directly enabling LLMs to generate patches, explicit patch generation, for issues is less effective than having LLMs edit the code repository, implicit patch generation. While CodeR achieves 28.33% resolve rate, RAG plus GPT-4 and AutoCode Rover only solve 2.67% and 19% respectively. Furthermore, we observe that existing LLMs may struggle to generate applicable and high-quality patches, as a correct patch requires strict format and is sensitive to line numbers, which LLMs cannot perfectly handle. The result also shows that CodeR sends more requests, resulting in increased tokens and cost at an acceptable rate. This could be due to our fine-grained design of multi-role and actions. The 10.33% improvement over SWE-agent plus GPT-4 reported demonstrates that pre-planning at the beginning of the pipeline is superior to deciding the next steps on the go. CodeR preemptively devises multiple plans in the form of structured graphs, and all agent roles will execute the predefined plan strictly according to the graphs. CodeR's leading performance also validates the effectiveness of this idea. Pre-planning also possesses clear advantages of bypassing imperfect instruction following and long context memorizing abilities of LLMs. Although CodeR has achieved impressive performance, we still believe that designing a more sophisticated plan will yield more significant improvements in the future. We also conduct ablation studies on 50 issues of SWE-bench Lite. The results in Table 5 show that removing the multi-agent and task graph would reduce CodeR's resolve rate from 22% to 10%. This further demonstrates that our carefully designed roles, motivated by real-world company collaborations, are highly useful for issue-resolving tasks. Additionally, we observe a performance drop and a cost increase when we remove the fault localization action, which highlights the significant potential of combining LLMs with traditional software engineering strategies for addressing complex downstream tasks. Section 5. Related work. Automatic issue resolving. GitHub issues can be resolved using the following solutions automatically. Retrieval Augmented Generation, RAG, is a straightforward approach which first retrieves the relevant code snippets from the repository, then prompts LLMs to generate a patch to fix the reported issue. To enhance LLM's proficiency in generating program patches, SWE-Llama was proposed, and it fine-tuned the Llama model on well-crafted patch generation instruction data. Following this, SWE-agent was proposed, which used LLMs to interact with the computer to solve issue problems automatically. SWE-agent predefines a series of agent-computer interfaces, ACIs, to enable LLMs to interact more efficiently with the computer. Additionally, AutoCode Rover expands the visible context information for LLMs by leveraging sophisticated code search tools in software engineering, achieving decent performance. Another work proposes a multi-agent pipeline of 2 successive steps. In the first step, 3 types of role agents, repository custodian, manager, developer, collaborate on the plan. The plan is represented as code and embedded into the main program for execution. After, 2 types of role agents, developer, quality assurance engineer, participate in the coding process. In this paper, we propose CodeR, which defines fine-grained agents, roles, and corresponding actions and incorporates advanced software engineering tools. Test-based automated program repair. Automated program repair has been an active topic in software engineering for years, and a majority of work can be categorized as test-based automated program repair. Given the presence of a test suite, generated patches can be validated against the test, making the result more trustworthy. However, a weak test suite allows test-passing patches to be incorrect, and a large search space makes it difficult to synthesize a correct patch. Therefore, various techniques have been proposed to guide the search process, including genetic programming, manually defined fixed patterns, mined fixed patterns, heuristics, learning from code or program synthesis, and semantic analysis. These works focus on code content, trying to find a patch that could satisfy all constraints, test, compiler, heuristics, etc., while ignoring the issue description itself, which may contain a lot of useful information. Apart from these approaches, many works adopt machine learning models to generate patches. SequenceR proposes a sequence-to-sequence NMT to generate the fixed code directly. CodeIt uses the same model to predict the code edits for the faulty code. DLFix, Coconut, and Cure take the context of the faulty statement as input and encode it via tree-based LSTM, CNN, GPT, respectively. ReCoder proposes a syntax-guided decoder and generates edits with placeholders via the provider-decider architecture. Reward Repair uses an RL approach that integrates program compilation and test execution information. Tear directly learns the typing rules to guide the generation. These works treat the APR problem as a neural translation task from the buggy code with context to the fixed code, and most of them adopt encode-decoder models. Different from these approaches, CodeR proposes a multi-turn framework that could collect necessary information on demand and generate the fixed code based on the information collected. Artificial intelligence, AI agents. The development of AI agents has made substantial strides, including many advanced methodologies to automate tasks. AutoGPT, AgentGPT, and MetaGPT employ an assembly line paradigm where diverse roles are assigned to various AI agents, effectively decomposing complex tasks in simpler subtasks through collaborative work. Diffie and FastGPT are LLM application development platforms that combine the concepts of backend as a service and LLM ops to enable developers to quickly build production-grade generative AI applications. Using these platforms, even non-technical personnel can participate in the definition and data operations of AI applications. SWE-agent enables LLMs to interact with the programming environment to automatically solve GitHub issues via predefining multiple ACIs. CodeR defines detailed and decoupled agent roles, e.g. reproducer, programmer, and tester, along with their corresponding fine-grained actions, e.g. reproducing, editing code, and testing code. Such an approach will facilitate resolving complex issues through collaborative efforts between various agents. Section 6. Conclusion and Future Works. This paper proposes CodeR, which excels at resolving issues. It demonstrates the importance of providing plans that mimic humans' problem-solving procedures for issue resolving. CodeR requires pre-specified task graphs that convert the planning task to a simpler decision task for LLMs and also provide a guarantee for the exact plan execution. With the idea of task graphs, some advanced software engineering skills like fault localization, mining similar issues, and web search can be seamlessly added to our predefined graph without any code changes by a JSON format text. CodeR's predefined plans are experiences provided by human experts. We believe it is one of the key factors in resolving issues. In the future, we will build a comprehensive set of plans that may resolve more and more issues.